Shri Gurubhyo Namaha. Namaskaram. So we're going to continue with our sessions on the foundations of secure software engineering. And in this regard, we are going into the uh, third video session. So if you have not seen the earlier videos, please take a look at it. And if so, with this, I move on to the Excel session. I hope you are able to see the screen. So we were discussing about the fundamentals of computer science and then moved on to the fundamentals of software engineering, where we touched upon the different aspects of the software engineering. We started with what is softwares and then why it is coming under engineering, and then the different aspects of software engineering, the fundamentals. So if you please take take a look at the video if you want to get revise that. So here we are now going to specifically talk about another important aspect of software engineering, which is programming languages. Earlier, whatever we talked about is more of a generic categorization of different kinds of softwares and how they belong to, how they are classified, and how they are being used. Now, this session is predominantly targeted to the software engineers who want to get into the programming, know more about the programming aspect of it. So, there's a little more technical in terms of the programming aspect of the software development life cycle or software engineering. Okay, so what is exactly a programming language? A programming language is a set of instruction. It is basically software, so which is a set of instructions based on a language syntax, just as humans communicate between themselves using one of the natural languages, which could be English, Tamil, Hindi, Chinese, German, or any of these languages. And so what are the fundamentals of a language is that the vocabulary, the syntax, the semantics are all equally standardized between the speaker and the listener, so that he is able to grasp the content which is rendered through a language semantics. So, for example, if I speak in Tamil, I will use the vocabulary of Tamil, or if I speak in English, I will use English-based words or vocabulary, and the person on the listener on the other side should be able to understand English as a language. So similarly here, when it comes to programming languages, here the one part has been the humans, traditionally, where humans create the program, and the code of the for the program, the software, and the computer is the one who takes it, understands it, and performs the instructions provided as part of the programming language, which is basically as part of the source code, where the logic of execution is defined. So so far these programming languages are generated by humans, but thanks to AI, now there is a new trend of vibe programming and other things, which we will touch upon later, where it is more computer co-piloted, or computer assisted, or computer generated softwares for the purpose of programming. Uh, so before we get into that, some basics about the different classification of programming. as such. So programming can be classified based on the level of abstraction, which means that how closer it is to the machine versus how closer it is to the humans. So the machine languages are more closer to the machines. They are more in terms of the binary language, which the computers of today understand. And so for us, it is more difficult to read or manage this code. Then there is a middle layer called as assembly language, which is also very technically closer to the machine, um, which use basically assembly codes, an abstracted layer over machine language, uh, but which is still not a very developer friendly language. Then there are the usual higher level languages, which are basically based on English based syntax or English based wordings or semantics. Uh, Another way of classifying languages is in terms of their programming paradigm, where they can be classified as a procedural language, where the thought process is around how you give the instruction is around you, or you create processes or procedures. So, and it is a communication between processes or procedures. That's how the language has been designed. The styling of the language is towards procedural thinking, or it is also called as procedure oriented programming. We'll discuss more about it. Then there is object oriented programming, which gave a paradigm shift to the way we are thinking. And instead of thinking as processes that communicate between each other, the language enables us to model objects communicating to each other. This is object orientation, while the earlier one is the process orientation or procedure oriented programming. Then there are specialized cases like functional languages, logic programming, scripting languages, concurrent parallel languages, declarative languages. Each have their own roles and responsibilities, and each are being used for different types of use cases. Then comes the difference based on the execution model of a language, which can further be classified into compiler-based language. What exactly it means is that certain languages, particularly these higher level languages that we talked about, they are, as we talked about, is more in terms of human understandable English vocabulary as part of the syntax of the language. But while computers understand more fundamental binary or machine language, so a compiler comes as a bridge between these two language domains, and what it does is that it compiles the source code, which is in higher language, and then converts it into a lower language like a machine language, which the operating system understands. So this is what a compiled language means. So there's a compiler between your source code and the operating system, and what the compiler does is it creates an executable which gets executed by the operating system. More about it shortly. And then there are interpreter languages where this kind of a compilation is not required. The interpreter based languages are executed line by line, directly by the system itself. So it need for every instruction is executed line by line, whereas a compiled language, it is executing at the level of a unit of execution is at the level of a file, in the sense that the whole file is compiled and converted into an executable. But here it is more of a line by line interpretation or execution. Then there is something called as bytecode languages, which tries to bridge the advantages and disadvantages between compiler and interpreter languages. So Java came about with its own bytecode definition, and while compiled languages are like C, C++, COBOL, etc. Interpreter languages are like all the scripting languages, JavaScript, shell script, uh, VB script, etc. TypeScript. And coming to the bytecode or compiled languages, Java is a classic example of that. C Sharp is an example of that, where they come in with the concept of their own virtual machines, which bridges the gap between an compiler and an interpreter based languages. More about it when we get into the respective slides. Then there are something called as just-in-time compiled languages. This is more in terms of, as I said, compilation does at a bulk level, or at a file level unit, which is a basic unit. But suppose in a real-time projects, we will have multiple files which can constitute a module within a project. And just-in-time compiler, I mean, traditional compilers, we have to compile the entire set of project modules every time a code change is made. But just-in-time compilers brings in the flexibility wherein I have changed only a part of the code, and only that part of the code has to be compiled in time. Uh, just when I need it, right? So that kind of flexibility is provided by just-in-time compilers. Then there are compilers specifically for declarative languages, for event-driven language. I mean, there are different types of languages, like declarative languages, event-driven languages, etc., which are more of higher level languages with a specialized focus on different use cases. Then, like object oriented programming, there are something called as aspect oriented programming. So this is just as we simulate real world objects in the object oriented program into a digital model, here we look into the aspect of a domain, or into the programming model. So we categorize things into aspects or properties or characteristics, and then model our programming style. Uh, so this is one classification of model, basically on how the execution pattern uh, changes. Then there are application domains, like general purpose languages, like the Unix C, I mean the C, C++, Java, etc. Then there are very domain specific languages which are used in specific domains. More about it when we get there. Embedded systems are unlike the other application programs which are which are supposed to execute um, at a laptop or a mobile level. Embedded system is more for a firmware or a IoT kind of a device, or the Internet of Things kind of a devices. So there are specific languages for web development, certain specific languages for data science, um, and languages for the scientific computing, etc. Okay, then languages can also be classified on a historic basis of their evolution, based on the first generation, second generation, third, fourth, fifth, etc. Each of them added an improvement over the subsequent over the previous generations. So with this, we move on to the next slide, where we discuss about the different generations of languages, their historical context. So the first generation language, I mean, can be traced back to the 1940s, where the raw machine code was used. Binary, it was more of a binary kind of instructions. Okay, and these instructions were done directly at a CPU level. That is, this is even a uh, what I would say, operating system era. Then there came the second generation languages between 1950s and 60s, where there were one level of abstraction called as the assembly languages, which provides the same mnemonics for machine code, but it is not directly the ones and zeros of the digital language, which is not binary. It is little more, what to say, the English symbols are being used there. Okay, so the third generation languages became prominent around the 1960s, where there were more of higher level procedural languages, like COBOL, Fortran, etc. Even C, Python, Java, which provide um, procedural language paradigms. Of course, here certain languages like Java and Python can also be provided as a object-oriented languages. So they bridge the gap between both. Uh, then there are the fourth generation languages, where more of domain-specific languages evolved. Um, like MATLABs, which is used on the data science side, and SAS for the analytics, business analytics side. Then finally, we are into the fifth generation, which started with the 80s, where more specializations of different kinds evolved. So if you see in these milestones, right, I think C played a very, very important role as part of, historically speaking, most of us would at those times were programming in C because it provided a very powerful uh, um, programming uh, controls, and so it also provided both application level controls, and also we can we can do systems programming with C, wherein you can actually talk to the underlying layers of the operating system, like a kernel or within the Unix or the Windows kind of operating system. So it provided a very powerful way of programming. And then there were languages like C++, which brought in the object orientation to the mainstream. They are very powerful languages, which helps us in modeling reality in on an object oriented way. And Python, which started early, but which is even today one of the most popular languages. We can call it as the Jambavan of uh, what to say, the programming language, or the Pitamaha would be a better analogy. So right from the early, I mean, at least for 20-30 years, the role of Python has been going stronger. Okay, so moving on, whatever we have been discussing, where we saw the evolution of how the programming started from direct machine language, which was closer to the machine's way of understanding things, and then we moved on to the first level, second level, third generation, and the fourth, fifth generations, where the language syntax is more human readable form. Okay, but yet these languages have huge um, learning curve attached with them, because they follow specific syntaxes and uh, rules and definitions of how each of these user defined functions, or the libraries, or of the syntax constructs in terms of data type definitions, or in terms of the construct loops, or how to create functions, how to program for interprocessing, or for multi-threading. So there's a huge comprehensive learning required to master these languages. Um, so that's why there are always specialists like Java specialists, J2E specialists, C++ specialists, who are a very strong grip on how the language is designed, and how best to use um, the features of the language for specific use cases. So it is the skill set, which is both an art, art as well as sciences, has been acquired through a rigorous practice and learning. Uh, However, in the thanks to AI, there is more of a natural language processing, wherein these specialized learning curves are less dependent, where the machines which are artificially intelligent, or which we call it as today's jargon as the agentic AIs, agentic artificial intelligence, which will substitute some of the complexities in remembering the syntax styles, and uh, generate these languages on behalf of humans. So this again, if you see, there's an evolution in the programming languages. So the original era, where we used to create this program, the source code of this program through text editors, like a VA editor in Unix or Linux. or in a text pad or a notepad kind of environment on a Windows operating system. Okay, then when with the advent of graphical user interfaces and the Windows environments, etc., more powerful or sophisticated integrated development environments, which we call it as IDEs, became more popular, wherein it helped us to generate they are more like code enablers or um, uh, application enhancers, where unlike the earlier text-based coding, where for example, when I started my coding in the 90s, or there was not much of internet access available for an ordinary programmer. So the internet was technically there, but it was very expensive, and not even corporates or companies had widespread use of internet. It was restricted to specific use cases, and it was basically rationed kind of a things. Second is that those days. To understand a new language, like I started with C, then I moved on to C++, then to Java. But this learning curve was not as easy as it is today, because one, as I said, there was no internet for which will help us learn faster with direct access to all the websites on specialized knowledges about on these domains. uh, Second, there was not even printed material available as textbooks for this, and if at all, if those are available, they were morely I mean under very expensive, because they were under foreign publishers, and they were not available for most of the developer community. So I remember where we somebody who would have had a copy of something on some book on C or C++, and we most of us, we used to go and take a Xerox print out of specific pages from there, and that through which it will help us. Uh, uh, then there were text-based manuals available as part of the language kit, which has just provided the syntax. Then, with the advent of IDE, the online help became much more powerful. All I need to do is press a help menu option, select it, and it gives me support on syntax. Then, from a raw support of syntax, it becomes syntax generative IDEs, where it use the technology called as type ahead. So by the time I start filling the syntax halfway through, it will help me complete that syntax. So I don't need to remember the exact syntax, what are the parameter styles, etc. The IDEs helped it. But all this was again based on generating languages which are the fourth or fifth kind of generation languages, which needs uh, a learning curve on the basic syntax, because unless I understand the fundamentals of that language, it becomes very difficult to code, even irrespective of what kind of IDE I use. Uh, So, however, with the advent of what we'll call it as the software engineering 3.0 era, we'll discuss about what that era means. But with the advent of or the evolution of artificial intelligence, particularly the generative intelligence and agentic AI, where today there is what is called as the vibe programming paradigm, wherein the computer assisted software generations are available. So, in other words, what we need to do is, as a programmer, I need to provide uh, instructions through natural languages, which are more like prompts to the artificial intelligent system, the agentic AI, and that agentic AI will generate on my behalf the actual fourth generation or fifth generation source code. Like it will generate a code on Python or JavaScript or C or C++, depending upon what kind of what instructions I give. So this is where the NLP is becoming the new era. So this is called as the prompt engineering era, where we prompt my way through software development. So where I give prompting is a way by which I give instructions. I prompt the instructions to the AI system to start generating the code. So the prompting take becomes an art when it becomes more context sensitive, because the programming the way I do is to be is to a specific context of the software that I want to build, based on the requirement for that software, right? So that so from programming, prompt engineering started with basically a querying system for generating reports or generating resources for research and other things. But when you wanted to generate more fine-tuned code, or fine-tuned research, it moves to what is called as context engineering. So if you add context sensitivity to your prompting, it becomes context engineering. So we will discuss more about that as we move along. Okay. So from the 2020s, the major inflection point is that from the traditional way of human generated fourth or fifth generation languages, we move on to the AI generated languages, either fully, partially, or partially. Okay, so that is taking us to the what will be the future. So we have been journeying from the past of the history of languages, how from a machine language to prompt engineering based language generation. If we extrapolate this to the future, experts talk about in terms of autonomous AI systems, where the entire SDLC cycle, including the CI/CD pipelines, management, etc., are now managed by AI agents, which are autonomously self-managing systems. And then the higher side is more of a cognitive programming. This is another major milestone where the roadmaps will lead us eventually, is in terms of what is called as a cognitive programming, wherein that instead of even directly prompting over over a text chat area, chat window, or through voice generated prompting, we can there are other ways by which the human brain and the computers are what or more integratively combined with what they call it as the digital singularity or transhumanism, where the brain instructions can be directly communicated to the computers. So those kind of higher level of um cognitive programming is in the future, but experts say we will be there soon, sooner than later at least. Okay. So again, let's classify the programming in terms of the shift that has happened due to the AI revolution that is currently happening now. It is taking the world by storm. One is the democratization of code. So like as I said earlier, there was a lot of need for uh, skilled programming experts. That means they should be masters in the specific language. So for several years of learning, practice and building a lot of softwares, they have mastered the specific languages, like C, C++, or Java. So we'll see a lot of Java certified, C++ certified programmers who have huge experience in real-time software building on these things, right? So there was an acquired knowledge over years of specialization. And that's how the market was. So these specialists had a huge uh, competitive advantage in the market, because they could demand a higher price in the market, etc. However, with the AI enabling the lot of software development life cycle, the dependency on human specialization is now shifted to AI, which in the larger context of things are economically more viable from the employer point of view. Uh, so the huge labor or the skill costs or the software engineering resourcing cost, human resourcing cost is dark is being addressed by these corporates today, thanks to all these AI technologies. So we need not for building, at least for most of the uh, what I would say, the mainstream websites, the front ending marketing websites, or even a e-commerce application, or which used to take couple of months to build. Today, with thanks to AI, there's not much of specialized skill, because there are standard design patterns, and there are AI support to turn around these applications quickly. So there is an accelerated development time. So one, there is not the dependency on specialized knowledge is reduced. Second, there is an accelerated development time. What used to take couple of months now is reduced to weeks. So if you what was 6 months is now can be done in 6 weeks. So what was done in 3 months now we can done in 3 weeks, or much even faster. With all this web programming, people turn around within week websites, right? So there is the accelerated development enables better time to market. Democratization of code reduces the total cost of ownership. um, no, from the employer point of view. Okay. So then there is a paradigm shift in abstraction, which is again providing leverage to to the specialists, right? Instead of they focusing on the actual low level syntax details of every languages, which is where their specialization evolved from. They can focus on the actual architecting, or the other aspects of the software development life cycle, where they can focus on designing better things, and let the computers handle the syntax and other learning. So this focus of shift also helps us upgrade in our in the hierarchy of what we are programming. And then the agentic systems are self-evolving. So all these things have their great pros. Of course, from the employee market perspective, or is employment security risks and other things, there happens to be some challenges in shifting our or in adapting to the new normal that the industry is moving towards. So that is a learning curve, which is part of any revolution or evolution. Uh, uh, so I think the smarter guys try to bring in their specialization. At the same time, they were able to bring in the leverage newer paradigms that are available in the industry. Okay, more about this when we discuss software 3.0. So this slide here provides a more context of the whatever we discussed. So I just want to, for example, from the 1940s to how the first generation languages evolved from machine code to assembly languages to procedural languages to domain specific languages to logical programming languages, like the fifth generation we talked about. And then the emergence of AI powered paradigm, wherein there is a lot of prompt engineering era, which is now evolving into context engineering, etc. Okay, so then there is the agentic AI systems, which helped in web programming and other kind of trends. Then going future, we go talk about the sixth generation plus languages, where autonomous AI ecosystems and cognitive programming, self optimization, neural interface driven programming. All these are in the larger roadmap, in the futuristic roadmap. Um, Okay, so this slide again provides the same context of how the languages are categorized under different heads. So there are query languages, there are domain-specific languages. We already talked about the other languages. Okay, then there are written and spoken languages. So unlike the traditional languages we have been used to, where we need to actually write code or the system will generate code uh, by prompting, which is also based on a written instruction. But now with, again, thanks to speech recognition and other AI related developments, so we can prompt through speaking, or provide the context that we need through natural language speaking itself. So that is where the even the prompting is now becoming easier, where all I need to is to just give them oral instructions and the computer picks it from there. Talking about the execution models of programming languages, which we touched upon earlier, I need to highlight here once again in terms of the difference between compiled, interpreted, and the just-in-time compilers. So while the compiled languages, uh, as I said, are in a higher generation languages, which has to be translated into the machine languages. So there are compilers are kind of a middleware layer, which to which if you provide the source code, which is a higher generation language, so it compiles the syntactical verification. Compiling involves a syntactical verification of the source code, and then it creates the output. It creates is a executable file, and that executable file is what the operating system mm, can take it for actual execution. And so the compilers are actually language, operating system dependent. So when I write code in the language being C, but when I run it on a Unix platform, the compiler I need to use is a Unix compliant compiler, so that the executable that it creates is compliant to the Unix operating system. Similarly, on Windows, or on the Windows side, if you want to do something, I need a compiler which understands the Windows operating system and generates the executable accordingly. Okay, so whereas when it comes to, the another major advantage of a compiled language is that it compiles as a unit of code collections, unlike an interpreter, which is the second line item here, where it is more of the system will read one line, immediately executed line, and then only it will read the second line. So if a source code has, say, 5 lines of instructions, the first line, the computer will read the first line, execute it, read the second line, execute it, read the third line, execute it. Whereas compile language will compile all the 5 lines and then execute them as part of the execution cycle. Just-in-time compilers were evolved to bring the advantage of both compilation and interpretation-based languages. So the advantage of compiled languages is that one is that the testing is left shifted, in the sense that I don't have some last minute discoveries or shocks, because of in my source code, my syntax is wrong, or somewhere there's a typos in my syntax, etc. Right? The source code is compiled before it can be executed. So compilation checks the whether the source code is in compliance with the specific language, grammar, and syntax of that specific language. And if there are any deviations, it highlights it at that point of time, at the compilation time itself. So we fix it, and then the executable is compliant to the specific language. Okay, so there is no runtime surprises. So in a compiled environment, there are two environments. There is what is called as a design time or compile time source code, and the runtime source code, right? Or the runtime executable of the software. So compiler left shift the SDLC testing cycle to the design time itself. But the overhead of that is that it takes a extra layer of execution. We need an extra compiler software in between to it, and these compilers not only add execution overhead, and some of these standard or enterprise scale compilers have a licensing cost attached to it, etc. Okay, so then there is the whereas interpreter languages execute it line by line immediately, so the execution time is faster. Then just in time compilers bridges the both these worlds, wherein it creates the bytecode which can be understood by middle layer, which is called as a JVM, or I mean a virtual machine. And that virtual machine is what I lift and shift and run it anywhere. So the today's the Dockerization or containerization all started with these bytecode logic, where I create a VM instance which contains a virtual version of the source code, which the underlying virtual machine understands, and that can be ported to any operating system. And so it is Java came up with the idea of what is called as write once and uh, uh, write once and execute it multiple times, or execute it anywhere kind of a time. So Java became an instant success there. C Sharp provided, which evolved post Java, um, provided the same solution from the Microsoft environments. So compiler languages and interpreter languages, these you must understand from a technical perspective. Although today there, I mean, uh, computer generator, AI generator thing, you may feel that you may not need these details, but it definitely makes you, I mean, wiser in the way you design your applications. So at least the basics you should know. So we already talked about some of them. So your compilers are pre-compiled libraries, so they execute faster. So in that sense, so while an interpreter is still having its higher level language, and it's run before running it, runs it. Suppose I have a JavaScript or a shell script running. I want to run it 10 times. Every time, though my shell script syntax is in English, it has to be converted into a machine language format compiler for every instructions in that file every time. So it takes more time to execute. Whereas if you talk about compiler based language, because it has pre-compiled the source code into an executable form before their actual runtime. Every time the syntax verification or syntax checking which the computer has to undergo before executing is avoided. So that way it is faster. Then error detection, the syntax and semantics error are caught at compile time itself. We talked about so this left shifting, which the compilers provide. So while here the only during execution the system able to identify these errors. So portability is again, compilers are less portable because they are language specific, as I said, and they are OS specific. So I need a specific compilers for that kind of an environment. C++ compiler for Java, for Windows, or for Linux, or for Unix, etc. Whereas if you take the shell script or JavaScript, they are neutral across these environments, because they are more portable. Whether I run my JavaScript within IE browser, in Microsoft Edge browser, or a Chrome browser, most of these browsers recognize this. Of course, this also took an historic evolution in the way JavaScript got standardized. Um, then there are speed based native execution. Again, we talked about earlier. Securities are also better in a compiler based languages because it provides you the binary obfuscation. Then when we talk about development life cycle, because compilation is a very strong layer in the SSDLC cycle, it adds to a longer life cycle in terms of the first fit of the solution to the production. But if you do look at a larger picture of the SDLC over here, because you are left shifting your testing, the SDLC cycle can be reduced. Interpreter based languages are quick for rapid application development, where which is the scenario for or the need for developing most of the websites of today. Where I mean, earlier we used to take months. Now within weeks they want, and they roll out to the market earlier to capitalize specific events, or faster time to market always provides a competitive business edge. So there's a lot of need for quicker turnaround. So that's why today there's a lot of need for full stack based developers, more rather than the traditional compiler based development. Full stack based technologies are predominantly using JavaScript kind of language for generating cutting across all the layers of the stack, from the presentation tier to the API tier, to the database tier integrations. And JavaScript is quick and simple to learn, so it is easier to build this one. So both these language types have their own advantages and disadvantages, and depending upon the specific use cases, uh, uh, we need to select the kind of language that is best suited for those use cases. Okay, we'll discuss about that as we go along. So compiler based workflows, we have lexical analysis, syntax analysis, semantic analysis. So there are multiple stages before the compilation completes and executable being created. But interpreter-based languages skips some of these stages. So, for example, there are close to 7 levels of processing needed at a compiler level. But when it comes to interpreter, it is not the case. I remember in those days, as part of your academic engineering curriculum, compiler design was a separate subject as part of the BTech or B computer science courses, um, where how best, suppose we want to design a compiler, how best to design, what are the design principles behind a compiler, etc., was a deep dive study there. Okay, now in today's hybrid model, which are technically called as a polyglot model, there is no one size that fits all. So no, all these programming languages come with their own pros and cons. So depending on the specific use cases, developers or the architects select the languages appropriately. So this is again one major point I want to share with you. Unlike in the earlier world, where the developers used to say, "I am a specialist on one language," and they will be very focused only on that language. I mean, their interest in adapting to the newer languages or working on newer projects was lesser, because they wanted to build the specialization in those languages. But that era is gone. So they don't today industry doesn't need specialists with several years of experience built over on specific technology or language. They need more smarter engineers or architects who can adapt to the newer technologies, and who have a more wider spread of expertise built, cutting across different languages, so that in a polyglot model they are able to adapt to any new technology, and start leveraging that in their SDLC life cycle. So we were seeing the difference between compiler, interpreter, and bytecode kind of languages, just-in-time compilers. So another major classification that we should be aware of is the procedure-oriented and object-oriented, which also we touched upon briefly earlier. So in a procedure oriented is typically like how processes communicate between each other. So the way as a programmer I design my code or I write my code is in terms of it's oriented towards process to process communication. So the classic examples you include C, Pascal, Basic, COBOL, etc. Then there evolved another paradigm which is called as the object-oriented programming paradigm. With, so while the earlier one was called as process-oriented or programming or POP, the object-oriented is called as a OOPS technology. So OOPS technology is philosophically very interesting in the sense that it uh, the the programming style is oriented towards the objective reality. In other words, it tries to digitally emulate or digitally model a real world objects. So the way we uh, design our code itself is based in terms of object. That's why it is called as object orientation. So I mean, when I started as a C programmer and then moved into C++, and I mean, I was philosophically attracted to that language and the power it brings, and I still till today I'm a big fan of C++. And from C++ I moved on to Java with J2E, and so those languages are provide the best of the world object oriented programming constructs, or the way of modeling objects in the digital world based on real world objects. This I would say is one of the pre-runners for content modeling in AI space, where ontological modeling of the real world uh, into the digital world, the highest end of it is what we call as the mind uploading, where the real world objects are simulated into the software hardware side of the computer, or into the artificial intelligence domain. um, and the A digital twin concept, where for every physical object there I can create a digital twin on the site. All this evolved from the concept of object orientation, where the physical object is digitized through by in my orientation. But you should remember that these languages are I mean, this object orientation is at a programming language level. So today, when you talk about mind uploading, it is at a higher level of abstraction, but earlier was at a language style. Okay, then there are scripting languages like Python, JavaScript, PHP, etc. Then multi-programming languages like JavaScript, which provides the advantage of both kinds of what to say, procedure-oriented and object-oriented languages. Of course, Python also comes here. So programming paradigm in terms of the procedural languages, core paradigm is the procedure centric. We talked about it. The program structure is more of linear flow when it comes to procedural languages. Core programming style is object centric or object orientation, where we talked about in terms of entities with a state and a behavior. This is again precursor to artificial intelligence of mimicking natural intelligence into artificial intelligence. Every natural intelligent object has a state or a property which is called as the data in digital world, and it also has a behavior. That means if I take an object like a chair, or if I take an object like the laptop, it has properties like its weight, or the color in which it is made, the brand, towards the memory capacity, the hardware capacity, the CPU.
etc. So these are all what I would say as the properties of it. And then there are the states of it: state, property, and behavior. These are the three dynamics of any real world objects. So then it is in a state. Different states for an object, like a state, an object can be in a switched on state. For example, my laptop is in a switched on state now, and after some time I will switch it off, so it is a switched off state. So it is in a different it undergoes different state transitions, an object. And another thing is it also have different functionalities or behavioral patterns. So with the laptop I can do certain functions, or certain it exhibits certain behaviors at a higher level of objects. For example, if I use a laptop, it is used for me to create new softwares, etc. Right? It has a specific functionalities. If I take a mobile, it will help me calling my friend or family. So if I take a camera, it has a specific function. So when I am modeling these objects in real objects into the digital world, it helps object orientation helps me create entities which symbolize the properties of the object, the state transition of the object, and also the functionalities that object can perform or is performing. Okay, so that is a major change in object orientation. Then the program structure, we have a linear flow, as I talked about. Here it is more of interaction with objects. There it is more of a process to process interaction, which is more linear. Here it is more of object oriented interaction, like object A talks to object B. And again, if you take it to the latest trends in AI, the agentic AI, where today we have the Google's agent to agent intercommunication, right? So in every agent, I would say an object in OOPS is a precursor to an agentic AI, where an agent knows the properties. It has a state transition flow, and it is an agent which can execute, or which can perform functions. Similarly, an object at a object orientation level, at a object model within a programming language, also provides that flexibility. Okay, so I mean, this is I mean, I always compare these lines, because there is a daughter line of evolution, right? We keep evolving. We started, our design thinking was in terms of object oriented programming, and today we have come evolved to a stage where we can create agentic AI, right? So the difference is in more of degree than in kind, as Swami Vivekananda used to say. So then there, when it comes to the data security, procedure language, because of its historic reasons, they have provided a limited way of security at a programming level again. Because all the data, there was a segregation between your code, source code, the executable part of the source code, and your data part. So they were not tightly integrated or logically interbundled. Whereas in terms of object orientation, they again simulating the real model, real objects, right? Like every object, the state data and its behavior is bundled together as one class or one object instance. So there is that level of security, like that for this object, this is the behavior, this is the data, and this is the kind of state transitions, right? And another beauty of it is that you can provide encapsulations and abstraction layers, layers of abstraction, right? Which means that an object, in the real, just as in the real world, can provide filters of how much of information about that object can be revealed to another object. And similarly, from the other object perspective, how much of it is willing to receive, right? This is called as encapsulation and an abstraction, which means that every object decides how much to what information to provide, and every object decides what information to receive. Okay, so again, taking a real world example, suppose I meet someone and I ask him to tell something about himself. So from his point of view, he will say, I mean, if depending on the environment, or depending on the particular context in which I am asking and who's asking. For example, if this question was posed at a corporate level to one of my reporting engineers, or one of my team members who was recently joined, he will provide an explanation to my question, tell me about yourself, more from his professional or career or his academic experience that he has been carrying on, and how he has come here, and etc., right? But if the same question I ask in a more an informal way, in a managed party, where I meet a friend, or a remote or a distant relative, and I ask him some questions, the way he responds might be different, right? He provides more personal information there, while in this case it is more of professional information, right? This kind of what to inform and what to receive is what is called as data abstraction, right? So that data abstraction can be handled both at a receiver level and the sender level. We saw about the speaker level, or one shares information, how much he has to share. He can provide filters, like saying that this information is very sensitive, I will share it only to my relatives, or my friends, right? The second thing is that these are more public information, it is publicly available, anybody can use it. Okay, so that level of categorization I can make. So that is called as uh, that is called as private, protected, and public kind of information access flow. So in a private access flow, that information I don't share it to anybody, not even with my inner I mean to my parents or to my children. So basically, when it comes to inheritance, which is a real world model, where I inherit properties from my parents, and my children inherit from me. The similar concept can be emulated in an object orientation style, where it provides different kinds of inheritance, single inheritance, multiple inheritance, etc. So when I inherit that, I can restrict that this information is private to me alone, or to my own object members, which is my functionalities, which is very sensitive to me. All I can extend it to my family members, my inheritance hierarchy. Or I can say that this is information is public. So this is called as private, protected, or public. Private is exclusive to that class. Protected is for access to that class and its inherited hierarchy. And when it becomes public, it is accessible to all. So this is again a real world example. Another major example, I mean, which I'm a big fan of, is the concept of friends, particularly in a language like C++, where it simulates a real world human psychology, where a lot of information we don't even share it to with our inheritance hierarchy, right? With our own family members, or with our parents, or with our children, but we are more than happy to share it with our friends. So that kind of what I would call say psychological intelligence is modeled in a language like C++. I'm a big admirer, which is a real time scenario, which most of us do it in certain ways or certain capacities at different points of time, right? So all these kind of levels of abstractions or levels of security can be built in terms of programming languages. Then there are other error handlings, etc., which are more sophisticated in object oriented languages. Okay, so the representative languages are C, Pascal, Fortran, Basic, etc. Java, Python, and C++, etc. fall under the object oriented languages. So ideal use cases, programming languages like procedural, where add historic use cases, and then in these days more restricted to systems programming, or for mathematical computations, gaming, creating software gaming tools, etc. Okay, object oriented programming is more for on the business applications, where you deal more with the real world objects to interact with the or end user applications, enterprise software, middleware software. All these things are part of the object orientation. Of course, these are all not hard and fast rules that this is the language you have to use for this kind of a things. This is more of a basic pattern of uh, or norm. So this is again a syntax level explanation of what we discussed. Here in procedure oriented language like C, the variable and function, the and the data, I mean the data and the function are separated. I cannot embed data within a function or the other way around. So if I take a structure, C provides structures where I can create data variables, different data types. If I want to create a structure called computer, I can have different properties of that computer, the brand property, the memory property, so different values that I capture, but I can't have functions as part of that structure. Whereas when it comes to Java or a C++ language, I can embed both the property and a method. What no, what methods can be used for accessing that property, and also I can provide an levels of encapsulation, like I can make that data uh, private, and it can be accessed only by one of the methods that I expose. So and I know what how to handle it. All the validation logic I handle as part of the method, and this whole thing is bundled as one class, so that this data cannot be directly accessed uh, mm, uh, or manipulated. It has to be handled by only the method that I expose, where I provide all the checks and balances before manipulating the data. So I have a better control in which the way I am programming. So from pops, oops, evolved from oops. Then there are more functional languages, which are higher specialized languages, and then we have, mm, I mean, agentic AI or artificial intelligence generated natural languages, through which we are moving towards. Okay, this is again different use cases where different kinds of languages can play for high performance computing and game engines, etc. C, C++, Fortran, Julia kind of languages are there. So Fortran, for example, most of the scientific science and technology related core R&D related thing, they use a lot of Fortran related languages. Okay, here high performance is critical, so these languages provide direct control over your operating system, where we can have a pointer based you can directly access the kernel or the underlying shells and the underlying even device drivers, etc., right? So it provides a large control, and so when you can create high performance computing with these controlled power that you have. Then moving on, there are languages which are specific for high assurance and safety critical things, like robust programming languages, IDRIS, etc. Which I mean, when you have more power, there are always the risks that you also comes along with it, right? For example, C provides you direct control on to the operating system, right? It provides you a lot of power there, but you can always misuse it. I mean, by mistake or mischief, and I mean, you can get into memory mismanagement, CPU utilization mismanagement, etc. But most of these things are addressed at a higher level of abstraction provided by the higher generation languages, like the Rust, Ada, or IDRIS kind of languages. And if you want to build a typical website or web based J2E kind of application, which is on Java, or you can use C sharp for .NET applications, etc. So these are all for regular web backend or mobile based applications, or also for building the middleware layer of technologies, where I want to build an API tied regular for content management, securities management. The entire tiers of software ecosystem, we have a lot of middleware components where I need to integrate with an SAP system. I need to build my own rules engine system. So all these things can be built with languages like Java, C++, etc., where they are very strong flavor. But when you want to build more of a front end web facing application, we want to build quick and dirty applications which have a very early time to market demands. JavaScript and its newer version of TypeScript, which provides you the data type feature enhancements, which was typically available only with the compiler languages, is now available within the JavaScript languages. So Elm is again a newer languages which provides a reliability in terms of execution. So then when there are specific cases like Python languages which have a very important role in data science, particularly on the machine learning, deep learning kind of thing. And today, I mean, Python has almost taken the AI world by storm, right? Today programming, just as the full stack has taken the web development by storm, Python has taken the entire AI generation, agentic AI, and other kind of RAG development, or all these things. Ecosystems is now Python driven, because Python today provides the largest available library, open source and library ecosystem, where I can plug and play multiple things at a time. I can build a system application, I can build a website, I can build a mobile application, or I can build a machine learning application, or I can build a agentic AI application. Python is almost cutting across all layers of programming. It is like the Bhishma Pita, which not only stood that strength of time, which is there for almost 30 years now, and probably growing stronger, and its demand has never come down. It has only increased, right? And it is also cutting across layers. I can build any kind of application using Python for most of the use cases. Of course, there are more complex use cases where other languages will be preferred, but in general, Python is today very popular because it provides, yeah, I mean, a wide variety of library infrastructure, a library of plug and play infrastructure, and it is very quick to learn today. Other domain specific languages for machine learning are languages like R, which became very popular, but now there are a lot of more Python based development than R. Then Julia is another language. I'm not much used it, or okay. So for rapid application development, Python, Ruby has a framework called Ruby on Rails. Then there is a Groovy kind of. So these are all development for rapid application development. What we call it as a RAD, right? Where people want to build solutions quickly. There are a lot of tools available, like Python helps there, full stack helps there. Okay, when it comes to the text-based language for text extraction, etc., I mean, there were some powerful languages right from the 1960s, where the shell programming became popular. Like K shell, Bash shell, etc., different shells, they provide a very powerful set of tools and commands for text extraction. Awk and Sed are all subcomponents, or languages, or models within the, or modules within the shell scripting space. So Awk or Sed are very, very powerful for text extraction. Then there came a language which is called as Perl, which I mean, most of us would have used. I mean, those of belonging to that era would have used Perl for a lot of text extraction and pattern matching, etc. Okay. So then Groovy is another powerful framework for building a lot of rapid prototyping, etc. So these languages helps to create quick MVPs, quick prototypes, quickly extract text and come up with some outputs, etc. So this is a laundry list of some of the popular languages, providing their historic context and um, who created it and when it was created, etc. This is just as an information. Okay, this is a summary of what we discussed: high performance languages, critical systems, web front end, web back end kind of thing, data science, scripting languages. What are the different parameters in which you can weigh across your tools and technologies, like concurrency model. Okay, the availability of ecosystems, the availability of development speed needed, the safety and security, and the performance and control, and the skill set availability in the market, etc. All these parameters will help us decide on the programming language that we wanted to recommend or use. So this is again a continuation of the different use cases. Front-end applications, JavaScript, Dart, or HTML are the best favorite these days. Okay, when it comes to mobile development, we can build a native iOS. It is on Swift, Objective C, etc. Okay, and there are some popular frameworks around it. Native, we have Android, Kotlin, and Java. Java was originally created by Sun Microsystems and which was acquired by Oracle. Kotlin is Google's customized version for Android on Java. So it extended the Java code base and created its own branch called Kotlin. Cross-platform like Dart, Flutter, which is again from Google, and React Native, or these are all again popular frameworks and languages there. Okay. Coming to the backend, today we can, for thanks to full stack, even backend can be done at using JavaScript. So Node.js is one of the most popular JavaScript frameworks for full stack development. Then, as I said, Python is again very popular use. Java again is more useful for enterprise softwares, not front-ending websites anymore, but more of building the middleware enterprise ecosystem. Go is more powerful today for high concurrencies and building quick microservices, etc. So C Sharp is part of the Microsoft ecosystem. Okay. So coming again to the database part, which again as part of the programming languages you should be aware of, there are different flavors of databases available. Unlike the traditional relational model, which has been running for the last 40-50 years and still widely used. There are today other alternatives on in terms of how you process the data, which and how you access the data. How you process the data is not necessarily in the relational model of tuples of rows and columns, or a matrix of primary key, foreign key matrix based on the chords, the principles of data normalization, etc., which has been the relational database specification for years, which is very schema dependent persistence model. There are again free schema or partial schema models, where like JSON model, or text free text model, or XML model. XML is more of a semi schema model. Schema is there, but it's not as strict as in a relational data model. Then there's a JSON, which is more free flowing schema. So the persistent schema flexibility is available today, and also the way I access the data. Earlier, the standard query language, the SQL, was the only means for actually querying the database or interfacing with the database. But now there are multiple ways of doing it. So the new paradigm was developed in the last 10 years or so, which is called as the NoSQL. NoSQL means not only SQL, okay, which means that it provides you the other ways of interfacing with it, and also it provides you other ways of persisting the data. So more about it when we talk about the databases, deep dive into databases sessions. Okay, and there are also models for representing a graph relationship in a multi endpoint graph relationship. Unlike in a relational model, there is a parent child one to many relationship. In a graph model, I can build a many to many relationship. All these social networks that we use today, if you take Twitter or Facebook or any of these things, there if you want to model those relationships, a graph model is ideally better there. So these NoSQL paradigms comes with a lot of those flavors. And while relational model is good for OLTP and OLAP use cases like online transaction processing or online and analytic processing, right? Because it provides you the transactional, particularly for OLTP, it provides you the transactional, or what to say, security through this commit rollback kind of interfaces. So I can build I mean, I can commit across multiple instances or multiple databases and then roll back a transaction. That kind of strength, which is very, very powerful or very much needed even today, particularly for transaction rich detail, particularly in the banking sector and other sector, where a financial transaction has to be either completely committed or rolled back. It should not be halfway left, because it will lead to a lot of chaos and financial loss, right? So that is the advantage of the traditional relational model. But the flexibility in terms of schemas, when I want to extend a schema or when I want to I have different ways of accessing it, are provided by the NoSQL, but they don't provide that kind of a transactional uh, security. So to bridge between the pros and cons of both these things and provide the best of breed advantage, there are a new emerging technology model called databases called as a new SQL, which is bridging the advantages of both traditional relational model and the NoSQL, and that is called as a new SQL. We will discuss more about it as we deep dive into the database sections. Okay, so again, this, as we talked about, I'm skipping this. Pros and cons also we talked about. Okay, so key trade-offs we need to decide as a designer, as a developer, or as a tech lead or an architect. We should be always trying to decide on these key non-functional requirement parameters, like what is the speed versus safety priorities, what is the flexibility versus structure priority, ecosystem versus innovation priority, concurrency models, okay, multi-threading, multi-processing, concurrency, etc. So depending on that, there are different language choices that we can leverage. Of course, all these things can be implemented in most of these languages, but some language provides advantages in some of these areas, whereas others provide in some other areas. So as a smart technology agnostic architect or a developer, you should give a very objective analysis of these advantages and disadvantages and choose what is the best need of your business requirements. Okay, so again, this is a high level recommendation in terms of web development. The React or JavaScript is popular. Mobile development, Kotlin for native mobile, Swift or Kotlin based cross thing for cross platform. Flutter is very popular. High performance, use C++ or Rust. Data and machine learning algorithms, Python is ideal now. And when it comes to AI, Python is available. When it comes to beginner path, Python script or JavaScript is easy to learn. Okay. So emerging trends, Rust is adopted more. TypeScript from JavaScript, TypeScript is becoming popular. From Java, Kotlin is becoming popular. AI development, which we'll talk about shortly. And web assembling is becoming very popular. Multi-language systems, as I talked, polyglot models are becoming very popular, where I combine multiple languages to achieve the same goal.